analysis class. Today we are going to proceed with where we stopped last time. So last time we were talking about in fact, we tried to see how you can show that a given operator is bounded, right? That is continuous. And we look at example 1 and then example 2, which is about the freedom operator. And in the first case, x was equal or is equal to y equal to the set of continuous function over the closed interval AB. And finally, the last one is the same, is similar to this one. That is the Fredholm operator, but the difference between the two is that x equal to y equal to L2, capital L2. That's the difference, meaning that the norm will change and the way you proceed is, will also be different. Yeah, you can see from here, L2 AB. So the operator is defined in the same manner, and the kernel is now assumed to be L2, right? If it is L2, it means that it is square integrable. That is, if we compute this one, which we denote by m squared or whatsoever, we can give it a name. If it's finite, it means that it's equal to a number. And we let that to be m squared. Because don't forget that its actual norm, you have to take the square root here, right? So the norm, the two norm of k is this with the square root. So if we square it, we have m squared. So m is actually the two norm of k. Now, in order to show that A is bounded, we use the Hölder inequality. Let me share what we did last time, where I defined the Hölder inequality. You will see that this one will be straightforward. If you use that. Okay, so let me first copy. I hope this Fredholm operator was already defined. So we quickly do that before moving to the so let me open a new window. Okay, I will change this. I don't know why it is not on the list. Reset. I noticed that. So see it disappeared, but I don't understand. I used it last week. It's no longer. I don't understand what is going on here. This is functional analysis, but I only see this pattern. Okay, let's see. But this is not what I'm looking for. Signal, no, it's not this one. No. It was here on the list. It cannot be this one. I don't really understand. Anyway, it was deleted. I don't know. Oh, it's really painful to realize that something that I've been using just disappeared. Just like that. Anyway, I will create a new page. There's nothing I can do. It's really unfortunate, eh? Anyway. Yeah, that the previous slide I was using have been destroyed, so they've been deleted. Anyway, you say x equal to y equal to L2 of the closed interval AB, and our A obviously we take f in L2, so it's a function. So we take, since it's a function, we take t in the interval AB because element of these are functions defined on the interval. So now we can do this, apply that to x, and that's what we have here from A to B, k, st. Now we take ds. S ds. So if you integrate with respect to x, it will depend on t. So that's exactly what we have. Okay. So we assume that k is L2 when it's L2 of two variables, right? Just don't forget it's a function of two variables. So it will be L2 of what? AB, Cartesian product, AB. That is over this. So if it is there, it means that the norm, the two norms of that is finite, right? So it means that the two norm, which is this absolute value square root e, that is the integral from A to B, double integral actually, right? Because it's a function of two variables, absolute value k st square. Now we have d dt ds or ds dt. Okay? And then we take the square root. So this is, oh sorry, it's norm of k. Eh? Norm of k as a function of two variables. And this norm of k is what we call m. And m is finite. That's what it means. If it's there, it means that its norm is finite. Okay, so that is it. So now, how do we prove that this operator A is continuous on this space? So we want to find a certain constant C positive. So this exists such that the two norm of this is less than or equal to that constant into the two norm of F. This is what we are trying to show, because you need to know exactly what we want to show, where we are going. If you don't, you will not be able to start. Now, this is the definition. The two norm of this means that I take this, I square it, I take the absolute value, square it, right? So what is the meaning of this? Remember the two norm of a function f, of course, is similar to this one. Is, if it's a function of one variable, like in this case, but this is, or you can even use the square, you can square to make it easy, so that you not apply the square root, you just square that. So this is the integral from A to B of the absolute value of f of whatsoever xt or whatsoever. Let us use x square dx. That is what we write. So if you write the same thing for AF, right? So we can say that AF square is equal to the integral from A to B, absolute value of AF applied to a certain x value. In our cases, we already put t there. Let us write t square like this, dt. So that's how we start. So we just take the absolute value of this expression, square it, and integrate, and see what we get. Right. So maybe a quick way to do that will just be copy. Maybe to copy like this. Oh no. Okay, so I copy and paste. So I write this. So I take the absolute value. So this is the absolute value, which is equal to this. So I put absolute value everywhere, right? And now I use the fact that if I have the absolute value of the sum is less than or equal to the sum of absolute values. So that's what I do here. So this will be less than or equal to, this will be less than or equal to the sums of the absolute values. So this is what we have. Now we have a good result. We have the grades that this is L2 and this is L2. You remember in the, that's why I was looking for the previous slide to show you where I wrote the Hurley inequality. You remember 1 over P plus 1 over Q equal to 1. Now you see that this is like our P, this is like our Q. We know that 1 by 2 plus 1 by 2 is 1. Sorry, it's 1. So this is our P. This P is 2, Q is 2. So 1 by P plus 1 by Q is 1. So, and they are L2, L2. So I can use Hurley inequality with P equal to Q equal to 2. So if I apply Hurley inequality to this, Hurley inequality with P equal to Q equal to 2. So please read, try to find from the video the Hurley inequality, and it's also in one of the tutorials. So in that case, this will be less than or equal to the 2 norm of this times the 2 norm of that. That's Hurley. Directly, if you apply Hurley, it gives us less than or equal to the 2 norm of this into the 2 norm of the other one. But we know already that this is finite because K is in L2, so this is finite. That's our M. And this is what we want, right? So this is our M, but first of all, we can leave it like, that would be, okay, let's see. So far, oh, okay. So far, it's only the absolute value, but you still need to compute this norm. So we need to square this and integrate, and finally take the square root to get this. So this implies that if you take the integral from A to B, absolute value of AF into T square dt, we square, that is, we squared this. If we square that, this will be squared, this will be squared. So that's less than or equal to 2 norm of k square into 2 norm of f squared, right? Now what have I done? Okay, I square and now I also integrate with respect to dt. So I integrate from a to b dt. Then none of this depends on t because they are constant, they are values. So if I take that out, it will just give us the integral dt from a to b, which is b minus a. So that will be b minus a into the 2 norm of k. Of course, it's square because that's what I take out. Now, if I want to get, but this by definition, this, which is that, is the norm af squared. So I will just apply the square root to that to get the result. So this implies that if I write this, I take the square root of all this, there's an equal to square root of b minus a into remember that what we wanted a factor of the 2 norm of f, which is here. So remember that this is what we are looking for. Right? And that is it. This is our constant c. We are looking for c. So we have found it. So this is this is our constant c, which is strictly greater than 0. Because b is greater than a, so this is positive, and this operator norm is greater than 0 because it's not identically 0. Remember that for a norm is 0 if and only if the operand of the norm, that is the function under the norm, is 0. But k as defined is not the 0. It's not 0, so that's positive. And that is it. We are done. So this concludes the proof. I mean, what we wanted to show. It's continuous because of that. So it's bounded. Okay, now the last thing that I want us to cover is from the slide. You see the thing with this software, you save something and the next day you can't open it, it's deleted. Oh, sorry. It's really frustrating, eh? Really. Okay, so that is it. Okay, that's what we did here. So that is it. Okay, now unbounded operator. Unbounded operator. So what is an unbounded operator? An unbounded operator is an operator that is not bounded, that is not continuous. That's all. So it means that we cannot find C such that the definition, as a norm less than a constant times the norm of the argument. You cannot find it. So let's look at this example so that you see properly what it means here. Now, if you look at the derivative operator, and we take its domain to be strictly included in L2, close interval, open interval 0 to pi into itself. And we take our domain to be C1, the set of C1 function of the over the open interval 0 to pi. What does that mean, C1? It means that continuous functions that are continuously differentiable. Continuously differentiable, when you say differentiable, I didn't say 2 times 3. When you just say continuously differentiable, it means differentiable once. At least once. Stop there with 1. Continuously, meaning that you can differentiate, the derivative exists over that interval, and the derivative that you obtain is also continuous on the interval. That's what the 1 means. C is for continuous, right? And 1 is the number of times that you can differentiate. Now, A is this operator. And we know that not all functions, you see, that's why it's strictly contained, because if you remember the definition of integrable function, a function might have a jump, but it's still square integrable. Right? A function with a jump, which is square integrable, is not continuous, because continuous functions don't have jumps. But you can have a function with a jump, but which is square integrable, in the sense that we define. So that's why the domain is strictly included. It cannot be equal, it's strictly included. And this is how we define it. And this is not equal to L2. So it's strictly included. And this domain is dense in L2. Okay, now to show that this operator is unbounded, we are going to do the following. We construct this sequence. Each of these S and T, these are functions called sequence of function. I defined that in one of the previous classes. And each of these functions is differentiable. In fact, you have the exponential function, which is not only in one time differentiable, but you can differentiate as long as you want. So we have already that advantage. So they are all in the domain that is C1 over the open interval 0 to pi. Of course, it's I here is the complex number such that I squared is -1. Now, if you compute the two norm of this, we know already that if I take the argument, I mean the modulus of this one, because the modulus of exponential is always 1, we'll be left with this, right? I don't know if I can write here. So this by definition, if you write this square, by definition is from 0 to 2 pi that is the definition. Now, the norm of this, if I take the modulus of this, it's just 1 by square root of 2 pi. It's the factor of E, whatever is there. Now, if I square this, it's 1 by 2 pi, right? And now, if I integrate this, I will be integrating 1 by 2 pi. But this is a constant, so if I take it out of this, will be 1 by 2 pi into the integral 0 to 2 pi dt, and antiderivative of this is t. So we take, so that will be 2 pi by 2 pi, 1. So that's why we have this. Even if I take square root of 1, it's still 1. Okay, so that's what we have there. right? Norm gives us 1. So all the xn's are, so that's exactly what it means, right? It means that this is on the unit ball there. So it's on the closed unit ball. It's not inside, but it's at the boundary on the ball. In fact, we call that a sphere. That's a sphere. Here you have the ball, that is everything inside. Now you take the ball, you remove the interior, you're left just with the shell, which is, in math, we call it the sphere. Sphere means just the shell, nothing inside. So that's what we have. So that's what we have here. So on the unit sphere, unit sphere. The radius is 1, it's there on the boundary. Okay, but if we compute AXN, what is AXN? This is our A. Now, if we apply AXN, A applied to XN means that we differentiate that once with respect to T. Right. Now, if we differentiate it with respect to T, remember that we take that and we put here. So that will be, if I differentiate with respect to T, it is I n, the factor of T, I n, to this, square root of 2 pi, right? And we multiply again. Right. And we know that in complex numbers, if I take absolute or the modulus of this, like that, this is a complex number, that's another complex number. So the modulus of two complex numbers, Z1, Z2, is modulus of Z1 into modulus of Z2. Now, if I do that, I know already that the modulus of this is 1, right? So this will give us the modulus of this, and this is a, so that will be n. So this is our an, right? Now, if we square it and integrate, that is, if you compute the two norms of this, if you compute the two norm of that, so obviously if we square this first like this, so that would be n squared into, right, that is the square. Now, if you want the two norm, I will integrate and take the square root. So this will imply that the two norm of xn obviously, what have I done here? Okay, there is t here inside, t, right? Okay, so what is that equal to? So now, if I integrate this from 0 to 2 pi, this is constant, it doesn't depend on dt, so it will be multiplied by 2 pi. So that would be m squared, right? And then I take the square root of that. If I take the square root, the square will not be there. So that's n that. So that is the norm, right? So it's n. So you can see that it is n. Of course, you don't need to put the absolute value because n is assumed to be positive, right? Of course, since this norm is 1, I can still say that it's times 1, which is times this. In fact, it is n. We have already seen it here. Oh, I see. Actually, that is the. Anyway, it was the first test. Instead of integrating, doing all this, that's another way. It is first test, I mean, to see this. Because once you differentiate that, you get this. So you can write that as, because you can write that in terms of xn. Because remember that when we differentiated, you still have this, but the only factor will be in. So I can write that is in. I could have written directly here that a, this is in into, so that's what was used there. Then if I take the norm of this, it will be the norm of this, which is actually norm of n xn. Then you can split that into 2. You take that out, which is absolute value of n, which is n, into this. And this is 1. So it gives you exactly the same as we did there. Right. Okay, so that norm is n, as we saw. And you can see that if I take the limit, it goes to infinity when n goes to plus infinity. What does that mean? If the operator A were bounded, we would have been able to find a positive C such that this less than C norm of xn. Because that is true for any. Remember when we apply the operator to x, we say that this is true. That's true for any x. If A were bounded, it means that we could find such a C so that this is true for any argument. And particularly if you take the argument to be this sequence, right? What does this mean? That is true for any x. And remember that from this one, if you remember the definition of the operator norm, the operator norm will be less than or equal to whatever constant is there. So the operator norm itself will be less than or equal to this C, meaning that it's bounded. That's exactly what we mean to say that an operator is bounded. That means that its norm is bounded. That's another way to understand it. So meaning that this is finite. All right. Now, if the limit goes to infinity, what does that mean? If this, when we take this norm, we take the limit, it goes to infinity, it means that I mean, if I take this ratio like that, remember, if I take this ratio, less than or equal to C. So if I take the limit, you see that it should be bounded. Should be bounded. But here, when we take the limit, it goes to infinity, meaning that if this goes to infinity, it cannot be less than a constant C. Actually, it means that this constant does not exist. So we can never find C such that this will be true. Because if it's true, the operator norm will be bounded, or this itself will be bounded. But here we see that it goes to infinity. So it cannot be bounded. That cannot be bounded. So since this goes to infinity, it means that I cannot find a C such that norm of this will be less than that C into an. So this C actually does not exist. So that is exactly what it means here. So therefore, it's unbounded. This is an example of an unbounded operator, meaning that this definition is not true. And that's exactly what we found. prove this. So if you want to show that an operator is not bounded, you just construct a sequence such that you'll be able to show that A applied to that sequence with the norm goes to infinity. That's all. Good. I plead with you to read this. I will not read this for you. I can only explain. Now, I will talk about this space. Oh, sorry. Now you see that we have a new space here. We have a new definition here. And the purpose of all this is just to show that, since we know that if we have a bounded linear operator, its norm exists. Right. And if I have two bounded linear operators, the sum of two bounded linear operators is a bounded linear operator. You can prove it. And if you multiply bounded linear operator by a scalar, it's still a bounded linear operator. That is stability. By these two examples, or by these two operations, stability by sum and by linear multiplication just prove that the set of bounded linear operator is a vector space. And besides, it's a non-vector space, because if you take, you know that each linear operator, bounded linear operator, has a finite norm. So you can define its norm as we saw in the previous slide. This is how you can define the various norms for in this linear operator. I mean, in this space. In other words, this space of linear bounded operator from X to Y is a norm vector space. It's a norm vector space, and the norm that we use is this one. This operator norm. And this is the definition. Calligraphic XY, the vector space of linear bounded or continuous operator from X to Y. That's it, that is that. And now the norm of an element in that space is defined by this. We know already from a previous theorem that all these norms are, this norm can be, you can use this for that norm, you can use that for the norm, you can use this for the norm, or you can use the inf of the constant C such that this is true for the same norm. So it's up to you to select which of the norm you want. But that's how you define a norm, the norm in that space. Now, if you take the space of bounded linear operator from X to Y, with this norm, it is a norm space. It's a norm space. Good. And you can prove it. Now, extra information that is an algebra. That norm space is an algebra. We know what is an algebra. That is a product like this of two linear bounded operator is defined by this one, and we have this inequality, that is the norm of the product is less than or equal to the product of the norm. So when you have this extra condition, you see that this space is an algebra, right? When you have a vector space that satisfies this for the element in the algebra, in the vector space, you see it is an algebra. We know that this is also true in the space of matrices. If you take the matrix norm, we know that with the matrix norm, this is also true. So if you take the space of matrices of a certain size, it will be an algebra. because of the. Okay. And we already mentioned this second point, that in a finite dimensional space, all linear operators are continuous, because, yeah, they are continuous. All linear operators are continuous. It's the same for matrices. If you take a matrix, the metric norm in a finite dimensional space, it gives you continuous. They are continuous, they are bounded. And obviously, you can define what is a Cauchy sequence in this space with that norm, and this is the definition. Exactly the way you define Cauchy sequence. For any epsilon, you can find an n such that for any n greater than that, you have this same definition. Okay, this is another result that I want us to oh yeah, even this one. I skip it. This property. Remember that here, this is the set of bounded linear operator defined from X into Y. Right. And we assume that each of these X and Y are norm spaces. Now, in this theorem, we are told that if the range or the destination space, this is a source space, this is a destination space, or the target, source, target space. If this target space Y is Banach, regardless of this is arbitrary, an arbitrary norm space. So you look at this to determine whether this is Banach or not. So if Y is Banach, the entire space is Banach. Right? Y Banach implies that the entire space is Banach, regardless of X. X can be arbitrary. That's the main result from there. But we know that R is Banach. So if we fix Y equal to R, you have a Banach space. So Lx, R will always be Banach, even if X is not a Banach space. And when Y is equal to X, we obtain what we call linear functional or linear forms. It depends on the textbook. Okay, so that is a good theorem, and we will use that later on to define what we call the dual of a space. Okay. Okay, so the next thing here is the bounded linear transformation. We have X, a norm space, and we have D, a dense subspace of X. And Y is a Banach space, and we have F, a function defined on the domain, which is a strict subset of X into Y. And this F is a densely defined linear operator. Densely defined. It just means that the domain here, D, this domain of F, because this D is the domain of F. And since this domain is dense in X, we say that F is densely defined. Densely defined. That's this domain is dense in X. And it's a linear operator. Okay, so if you have such an F, the theorem, this theorem of bounded linear transformation tells us that there exists a unique continuous linear operator F that extends F and that has the same norm. Okay, it's also, this theorem is similar to Banach extension theorem. We haven't covered that, but it's fine. Banach extension theorem, if you hear about it, it's a bit similar to this one. That is, you have a function defined somewhere and you can extend it to another function that has the same. In fact, that is the extension, meaning that that function, if you restrict to the domain, you obtain the original function. So you can extend it and the norm are still the same. So that's what you have here. You can extend this F all over the space. You can see that because D is dense, that's why you can extend it. D, the domain of F is dense on C. So we can easily, because it's dense, you can easily extend it on the entire space X to such a function. And the extension will have exactly the same norm with the original function F. So that is this theorem. Now the next, you see, I mentioned the dual space when I say that when Y is equal to R. Okay, but we do that. You can see here. When Y is equal to R, the dual space, now that's, you call it X star, which is the dual of X. But we'll talk about that in the weak topology later on. But what I want to do now is introduce the definition of in fact, this definition. Let us introduce the definition. That is a sequence of bounded the sequence of operator that is bounded at a particular vector. Okay, definition. So we have two norm spaces, X and Y, and we take a set, a sequence, a set or sequence. We say sequence, it refers to the subscript in N. Okay, so let's say a set or a family of bounded linear operator like this, bounded linear operator, meaning that each A sub I is an element of calligraphic X, comma Y. Now, this family will be said to be bounded on a vector. I have a family, and the family is bounded on a vector. It's not bounded everywhere. Each element of the family is already bounded. It's a bounded linear operator. Each A sub I is bounded. But now the family will be bounded on a particular vector X, right? Bounded if you can find a constant such that the norm of the family at that vector is bounded for any index. That is what it means. So this family will be bounded, that is, all the AI applied to X, if it's bounded on that. Bounded on that means that the norm of this is finite for any I, right, like this. So this family A sub I is bounded on this. Bounded, the family is bounded, meaning that the entire family is contained somewhere in a ball. So you can see that not the entire family, but the entire family applied to that same vector X It's bounded like this. Obviously, because it's bounded at that x, this c depends on x. So that c depends on x. If I change x, I'm not sure that the family will be bounded again because we say that it's bounded at that x particularly. So the constant will depend on x. It might be bounded on another element, let's say y different from x, with a different constant. That's why we say it is that constant depend on x. So I can, if I change x, and if the family is still bounded on a different vector, that c might not necessarily be the same. So that's the definition, because that definition will lead us to this Banach-Steinhaus Theorem. So we are preparing the stage, we are setting the stage to reach to the Banach-Steinhaus Theorem. Now the second definition. Now we are not talking about the family being bounded at a vector, but we are talking of the family being uniformly bounded. So for a given family, we have two possibilities: a family of bounded linear operator from x to y can be either bounded on a vector, or it can be uniformly bounded. So that's important. If I have a family of bounded linear operator like this, it can state whether it is bounded on a vector or if it is uniformly bounded. To be bounded on a vector means that I take all the operators of the family applied to that vector. If I take the norm, it's finite. Then on the constant that depends on the x, it's finite for any I in the family. So it will be less for any I. Now, to be uniformly bounded means that it is bounded without the x. Now you can remove the x. If you remove the x, you still have that inequality, and that c will not depend on x because x is not there. Now, if you remove the x from this definition, if you remove the x, we still have that. We have this, but without the x, you just remove that. It's uniformly bounded. That's the difference. So, bounded on a vector, we have this with x with the vector present. Uniformly bounded, I remove the x, but I still have that. I remove the x, meaning that even in the c, I remove the x. And this is still true. So that is the definition. A set of bounded linear operator is said to be uniformly bounded if we have that. So you can see that it's exactly similar to this, but we just remove the x. That is uniformly bounded. Now, Banach-Steinhaus Theorem, what does that state? Banach-Steinhaus Theorem tells us that if we have two norm spaces where the first one, x, is a Banach space, right? So x, the source space or the domain, not exactly, but the source space, x is Banach, the other one is a norm space. And we have our family of bounded linear operator, because remember, the idea of bounded on a vector and uniformly bounded is preparing us towards that Banach-Steinhaus theorem, right? Okay, so we have that the family of bounded linear operator. Now, we want to characterize uniform boundedness. This is what we want to characterize. We know already what it means. We have this without the X. Now we want to see what characterizes, what should the family satisfy for me to say that for certain this will always be true. That is the characterization, and it's given by the Banach-Steinhaus Theorem. So Banach-Steinhaus Theorem is about the characterization of a family of bounded linear operator that is uniformly bounded. So if I want to show that a family like this is uniformly bounded, what do I need to prove? So that's Banach-Steinhaus. So the family will be uniformly bounded, that is this thing or that. The family will be that if and only if. So if I want to prove something, if I want to prove that the family is uniformly bounded, it's enough for me to prove that it is bounded on all vector x from x, subspace. So if I prove that this is true for any x in A, so if I prove that this is true, if this is true, of course, for any I, and I show that for any x in capital X, this will imply that our family is uniformly bounded. That's Banach-Steinhaus theorem. So actually, it connects these two. That is, if this family is bounded on not a single vector, but all vectors of x, then it's uniformly bounded. Banach-Steinhaus. Repeat, we have a family of bounded linear operators from x to y. Such a family, we can define whether it's bounded on a vector or if it's uniformly bounded. Now, to prove that it's uniformly bounded, if we succeed to prove that it's bounded on all vectors of x, Banach-Steinhaus theorem tells us that it will be uniformly bounded. So that is the key idea about Banach-Steinhaus theorem. And the proof of that is based on Bayer theorem. You don't need to know the proof, right? Just have an idea what is Bayer theorem. It's based on that. We are not doing the proof. So what you need to know is the Banach-Steinhaus theorem. And we'll stop here for today. We might do a few examples of that, and we will dive next time. Maybe tomorrow I will record another one on the dual space of the dual space and the weak topology. Banach theorem, okay, and its corollary. We quickly say something about that. So if weak topology, so if we can finish the weak topology by the end of this week or somewhere beginning of next week, it will be enough for the program. It's true that there's another part for the program, but if we cover this, we try to cover this, and that will be okay for the program because we introduce the LP spaces that we covered during the first part of, in the beginning of the semester. We also had an impact to cover the entire program. So we will do that and cover the weak topology, and we'll do some tutorial, and that you'll be good to go for the oh, you still need to write test 2 before the comprehensive test. Let me quickly check here. Test 2 is on the 12th. Normally, the comprehensive test. When is the 12th? The 12th is just next week. Okay, we'll see what we can do. You can see I have test 2 online. I have a call. I don't want to take that now because of the class. Okay, so You can see have test 2 over the weekend, that is on Saturday or Sunday, depending on the week. But we need to cover something, and test 2 will be mainly on bounded linear operators. So we need to have some tutorial session, and by the end of next week, we need to cover necessary stuff so that you can write the test on the 12th. But that one, the comprehensive test will be a face-to-face test. Okay, I will stop here for today. Thank you for kind attention. God bless you. See you next time. Bye-bye.